Hi, welcome back. This video will be the last video for chapter 8, which will cover 8.3 factors affecting reaction rate. Here you have another 3 objectives in this topic. Let's start with the first learning objective, state the Arrhenius equation. So this is the Arrhenius equation. And then now, let's go through what's the meaning of this symbol. Basically, we already have the idea. The K is stand for rate constant, while the A is the constant which we know as collision frequency factor, while E is natural log exponent, EA is referred to activation energy, R is the universal gas constant, at where in this equation we're going to use 8.314 joule per mole per Kelvin, which is different from the one that we use in semester 1. And then lastly, the T is stand for the absolute temperature, means that the unit must be in the Kelvin. So when you plot the graph, because here is the exponent part, so the curve that you're going to get is a curve graph. However, we seldom use the original Arrhenius equation at the previous slide because this one have the power over here, which a bit difficult for us to do the calculation. So to make it more easier for you to do the calculation, we need to take natural log at both sides. So when this happens, we rearrange, it will become ln A plus ln E. Again, we move the power in front here, then we will get ln K equal to negative EA over RT ln E plus A. But due to ln E is equal to 1, so that's why finally we will have this formula, ln K equal to negative EA over R, 1 over T plus ln A. When we look at this, basically try to relate with the linear relationship, at where you will notice that ln K actually refers to y-axis, while the negative EA over R is the gradient of the graph. The x-axis is 1 over T, while the ln A is the intercept C. So then with this, we can plot the linear graph, at where also easier for us to do the calculation and plot the graph. Now let's relate the Arrhenius equation with the graph. So if you want to plot the graph, you are going to plot the graph ln K versus 1 over T. So here, because of this Arrhenius equation, you can see there is negative sign here. So that's why the slope of the graph is negative slope. Okay, then revise again. The EA is stand for activation energy, and then the R is 8.314 joule per mole per Kelvin, okay, which is different from what we use in semester 1. Okay, due to the unit of the gas constant is in unit of joule, so that's why later when you do the calculation, you have to make sure the activation energy will be in the unit joule per mole. Most of the time, the question will give us the activation energy in terms of kilojoule per mole, but we want joule per mole. Okay, if the question gives us kilojoule per mole, we need to convert to joule per mole by multiply with 1000. Then the T is represent absolute temperature, which the unit must be in the unit of Kelvin, and A is the collision frequency factor. Sometimes you will notice the question will involve 2 different temperatures. So if you have 2 different temperatures, basically you also will have different rate constant. Okay, so if we have 2 situations, we will label the condition as 1 and 2. Okay, so generally T1 is lower than T2. But then because we want to do the calculation, so it will be easier for us to use the formula 2 minus 1. Okay, that means we use the linear Arrhenius equation to represent higher temperature and for T2, and then lower temperature for T1. Or actually you can, either one is okay. Okay, but normally we prefer like give the T1 for lower temperature and T2 for the higher temperature. So let's continue with the derivation for combining the equation 2 minus equation 1. So ln K2 minus ln K1 will equal to ln K2 over K1. Don't forget this bracket, and then equal ln A minus ln A, so will equal to 0, or you don't need to write it down, is okay as well. Then the next part will be negative EA over RT1. Okay, we multiply in this so that easier for us to do calculation later. And then minus negative EA over R1 over T2. So minus minus will become positive. Okay, here minus minus will become positive. Okay, so plus EA over RT2. Then now I factorize the EA over R. EA over R. So we will have this EA over R negative 1 over T1 plus 1 over T2. However, we prefer that positive at the front, so it will become EA over R 1 over T2 minus 1 over T1. Okay, so in this subtopic Arrhenius equation, we have two formulas to remember. The first one is ln K equal to negative EA over R 1 over T plus ln A. So normally, we use this formula when there is only refer to the reaction happen at one condition. We will use the second formula if you notice that the reaction happen at two different temperature. So that's why we have T1 and T2. Basically, when we go for the question, which one is T1, which one is T2, is no problem. Okay. However, to make the mathematics easier to do, without the negative sign, we still prefer lower temperature is T1, higher temperature is T2. Then to keep in mind that here is ln K2 over K1. But then here is T1 minus T2. Okay, so do remember, memorize these two formulas. Now let's continue with the tutorial question number 8. The decomposition of hydrogen peroxide react with a rate constant 0.65 per molar per second. So rate constant is K. So this is the first rate constant that we make. We always make the practice is K1. At 400 degrees Celsius means that this is T1. If the activation energy 200.8 kilojoule per mole, this is activation energy. What is the rate constant? So they ask us the second rate constant at 200 degrees Celsius, means this is T2. Okay, then now we know that we have to apply the formula that we just derived in the previous slide, which is ln K2 over K1 equal to EA over R 1 over T1 minus 1 over T2. Okay. Now, we have no idea what is the K2. K1 given in the question is 0.65. EA is 200.8 kilojoule per mole. If you still remember, we did mention, emphasize just now, we have to convert this 200.8 kilojoule per mole into joule per mole. Okay, so when we do this, we will use 200.8 multiply with 1000 and then divide with the R. The R value that we need to use is 8.314 joule per molar per mole per Kelvin. Okay, then the next part, 1 over T1. T1 is 400, and then we is given in degrees Celsius, we must convert them to Kelvin. So it will become 673 minus 1 over T2. T2 is 200, so will be 473. So press the calculator, continue the calculation. You supposedly will get the value for the K2 is 1.67 exponent negative 7 per molar per second. How you know this unit? Basically is from here. Basically is here. We follow this one. So from this unit, we know that this chemical reaction is second order. Per molar per second is the unit rate constant for second order. Tutorial question number 10. The rate constant for a first order, so this question is very obvious. Let us know this is a first order reaction, is 4.6 exponent negative 4 per second. So this is K1. If the question didn't mention it is first order, based on the unit of rate constant per second, we also know that this reaction is first order reaction. At 350 degrees Celsius, so this one is T1. If the activation energy is 104 kilojoule per mole, so again we are given the activation energy in kilojoule per mole. So do remember that we need to convert them to joule per mole. Calculate the temperature. Okay, this is a bit different with previous question because previous question number 8 asked us to determine the rate constant. But now this question is asked us to determine the temperature. So it's T2, at which the rate constant is 8.8 exponent negative 4. So because we can see there is two temperature, so we are going to use the Arrhenius equation. Ln K2 over K1 equal to EA over R 1 over T1 minus 1 over T2. So ln K1 is 4.6 exponent negative 4, while this is K2. Okay, so K2 is 8.8 exponent negative 4. Okay, K1 is 4.6 exponent negative 4 equal to EA 104 kilojoule. We have to convert to joule, so we multiply with 1000 over R 8.314 and then 1 over T1. T1 is 350 plus 273 minus 1 over T2. We have no idea what is T2, so you can do the calculation. T2, finally you will get the answer is either you remain it in the unit of Kelvin. Don't forget, because you already convert to Kelvin, so the T2 that you determine 643.8 Kelvin, or you can convert this unit, this value, to degrees Celsius, 370.8 degrees Celsius. Tutorial question 11. Given the same reactant concentration, the reaction at 250 degrees Celsius is 1.5 exponent 3 times as fast as the same reaction at 150 degrees Celsius. So as we always mention, higher temperature we will make it at T2, and then lower temperature we make it T1. Calculate the activation energy for this reaction. Okay, so activation energy is question mark. So again, in this question, we have two different temperature. So that's why we are going to use the formula ln K2 over K1 equal to EA over R 1 over T1 minus 1 over T2. So, but when we look at this question, the question doesn't show us any value of the Rate constant, but they tell us that the reaction is 1.5 exponent 3 times as fast as the same reaction. Okay, so here we just can be simplified that K2 is faster, the reaction at T2 is higher, is the rate of reaction at T2 is higher than at T1. Okay, so that's why the ln K2 over K1 we can substitute with 1.5 exponent 3 equal to EA, we have no idea, and then over the R is the gas constant 8.314. 1 over T1, in this case T1 is 150 degrees Celsius. Remember, convert them to Kelvin. And then for T2 is 250 plus 273. So press the calculator, you will get the EA. The value that show in the calculator is in joule per mole. So you have to convert them to kilojoule per mole. The final answer is 98.24 kilojoule per mole. Tutorial question 14. Variation of the rate constant at different temperature is as follow. Okay, so that's me again. Here showing that at different temperature, the rate constant are different. So the unit per second, again, we know that it is first order. The unit of temperature always in Kelvin. Determine graphically the activation energy for this reaction. So when we are given like this, we know that we are going to use the Arrhenius equation, which is ln K equal to negative EA over R 1 over T plus ln A. So from this equation, we know that the y-axis is ln K, while the x-axis is 1 over T. So before we can plot the graph, we need to change the value in this table. Because in this table, the temperature given is in unit of K. So we have to convert to 1 over T, while the rate constant we have to convert to ln K. So this is the table that we're going to use to plot the graph. Based on the table that we get in the previous slide, we need to transform them into the graph. Again, this is the ln K is y-axis, 1 over T is the x-axis. So basically, you will get a negative slope linear graph. Okay, so here remember that if you look at here, this one is 0.001, 0.001, 0.001, 0.001. So here you will notice that in the graph here they have to mention 10 exponent negative 3. So that here you will show 1.1, 1.2, 1.3, 1.4. Then the scale will be more suitable, allow you to determine the gradient. So the slope that you determine over here is 2.3 exponent 4. Okay, we can ignore the negative because the negative is just showing that it is negative slope only. Okay, so when we refer to the Arrhenius equation, the EA over R means gradient. Okay, so the gradient that you determine from the graph, this one is determined from graph. Determine from graph, and then we compare with the EA over R. So R move to here, the relationship will become multiplied, and then the EA value is in joule per mole. Okay, because the 8.314 is joule per mole per Kelvin. But when we give the answer Actually, even though for this question, as long as you put the unit, then should be no problem. But you will notice that in most of the question, they prefer to use kilojoule per mole. So you can convert it to kilojoule per mole. So the final answer is 191 kilojoule per mole. Okay, now we briefly discuss the objective question. This question also from tutorial. We start with question number 6. If activation energy for a certain biological reaction is 50 kilojoule per mole, by what factors will the rate of reaction increase when body temperature increase from 37 to 40 degrees Celsius? So again, when we look at here, there is two different temperature. So basically, we know we are going to use the formula ln K2 over K1 equal to EA over R 1 over T1 minus 1 over T2. So in this question, we need to look for the EA value. R we know, T1, T2 also have the answer. And then, the EA is given 50 kilojoule. EA is given. What factor will the rate of increase? Okay, so that means we are not looking for the ln K2 over K1, but when you press this calculator, when you substitute all the value here, you will able to get the ln K2 over K1. But because of this question, it asks us what factor the rate of reaction increase. So then basically you need to find the ratio K2 over K1 so that you know the rate of reaction increase how many times. Okay, then now we proceed to question question number 8. The isomerization of CH3 and C follow a first order reaction. The half-life to be 16 minutes at 199 degrees Celsius, 12.5 minutes at 230 degrees Celsius. And then we need to calculate the activation energy. So again, two different temperature. We're going to use the formula ln K2 over K1 equal to EA over R 1 over T1 minus 1 over T2. So again, in this question, we are given T1, we are given T2. We also know the value of the R, but we need to determine the activation energy. This time, this is the question mark. So then we need to find out the ln K2 and K1. So how we get the answer? Because this question already let us know it is first order reaction. And then they give us the half-life. So we can relate the formula of half-life for first order, which is the half-life equal to ln 2 over K. So ln 2 is the fixed value. Half-life is given in the question. So we will able to find the value of K1 and K2 respectively. And then we substitute here. Then we can find out the activation energy. Question number 9. The rate constant at 25 degrees Celsius for a certain reaction is 3.46 exponent negative 5. And the activation energy is 106 kilojoule per mole. What is the value for the frequency factor A in the Arrhenius equation? So in this question, then it is very obvious that we cannot use the formula that we apply in question 6 and question 8. Because question 9 here only consists of one temperature, and they ask us to look for the frequency factor A, at where we cannot see any symbol of air in the equation that we apply in question 6 and question 8. So that's why we are going to use another formula, the linear formula, ln K equal to negative EA over R 1 over T plus ln A. So ln A is question mark. Temperature given, again, remember convert to Kelvin. R is 8.314 joule per mole per Kelvin. And then the activation energy also given, but don't forget to change the unit kilojoule per mole to joule per mole. So rate constant also given. Yes, so we only have one unknown, then we can solve this question. Congratulations that you already finished chapter 8, reaction kinetic. So we use 7 videos to discuss all the tutorial questions. And then next, maybe you are going to continue with the question from other sources, which maybe you need to identify it yourself, whether you are going to use Arrhenius equation, integrated rate law, or even differentiate rate equation. Thank you.